All right, let me jump back to where we were at there. Okay. Okay. This is an important subject right here. This is the 74X. And when I say X, it could be any other. The 373 is what they call a octal buffer. Right there. Latch. It's a latch. Right there. It's got an input that's called G, and this G simply means whenever G is high, whatever's on the input is passed on to the output. Whenever G is low, it's taken low, whatever was last there is kept there. It's a latch. It just holds it there. So what we've got here is we've got coming through right here, and AD0 through AD7 goes through one octal latch. A8 through A15 doesn't have to go to a latch on the 8088, but it does on the 8086. We would need another latch there. This happens to be an 8088 right there. If we're doing this, there should be another slide. Next one here deals with there. But we would need 3 of these latches there. So we have to latch this address there because the memory device or the I/O device needs to have the address the same time as it does the data or to write the data. So we have to latch the addresses on and keep them out there. And of course, the reason that they multiplex these address buses with the data buses is to save pins on the device right there. 40 pins at that time was a very large device. Now, if you look at some of these microcontrollers out there, the F120 Intel, the Silicon Labs F120 has got 100 pins on it. You know, if you look at some of the new microcontrollers, I think the i7's got somewhere around 480 pins, something like that. That's there. See, 40 pins was about as big as anybody made in the 1980s. That was before they came with ball grid arrays and flat packs and all these other new technologies right there. So as we look at this right here, this is an important slide. There should be another one here. Yeah, see, this is the one for the 8086, and you'll notice that it's got 3 of these address latches. So the 74 373 is an address latch, is what that is. And you need one for every 8 lines. So what we've got here is we've got our address bus going from A0 to A19, and it's coming from these lines here that are enabled right here, right there. So, and it just brings that signal out there because these status bits we're going to ignore those, but we still need to separate the address lines from them. Then this is our AD15 through AD8 going through this octal decoder latch. It's an octal latch, and this is an octal latch. You'll hear the term octal latch. Octal is the word for 8. Latch just means latching. The ALE is what's driving those latches right there. So I can almost guarantee you will have a question on the final exam is what is the purpose of the ALE? And it is to latch the address lines there in order to separate them from the data lines right there. So, and then we've got our control bus, our memory / IO NOT, our read NOT, write NOT right there. Those are our control bus. So that gives us our 3 buses that we have to connect this microprocessor to the outside world. That's there. So this is with the demultiplex address bus. So we have 3 buses that we deal with. And those buses consist of the address bus. Right there's our address bus. There's 20 lines on our address bus. There's 16 lines on our data bus on the 8086. And there's 3 lines on our control bus. The memory IO NOT, the write NOT, and the read NOT and the write NOT. Right there. So, and the ALE is also, yeah. G is just a gate. Yeah. Yeah, these were called, when this chip came out, it was called a gated latch. That there. What? Gate. Or latch, output enable. Output enable. That there. So we just tie that to ground because we always want the output to be enabled. If we tie that high, then we tri-state the output. Thank you for catching those pins out there. But G stands for gate because we can use this latch for other things. That there. And sometimes we want to tri-state the output if that particular chip is not being selected. For this application, we always enable the output. Output enable. And that's an output enable not. And the way you can tell it's not by this little bubble right there. This little bubble on the, whenever you see a pin with a bubble right here, see that little bubble right there? That means that the output is active low. Or that's actually an input. That input is active low. So when we tie that pin low, the output of this pin is, this particular device is enabled. And we'll see that output, that OE not, we'll see that a lot on our memory devices. Right there. So you'll see that pin quite a bit right there. And you should have seen these latches in your basic digital course, didn't you? Didn't you cover D latches? If you look at a basic, really the 74373 is 8 D latches. That's there. And somebody keeps wanting to call me during my class time. Right there. So there where I can just hit a button and say I'm in class. It's in the text message. So, okay, getting back to right here. So G is our gate. And that just simply says that when that gate is high, whatever is on the input is passed on to the output. As soon as that gate gets low, then whatever was on the input is now latched onto the output. It's there forever until we take G high again. And then as long as this OE not is tied low, the output is enabled. Since in this particular application, we just tie it to ground, it's always going to be low. Right there. So at some point, you'll maybe be asked to draw part of this or complete the drawing or at least explain what this is doing. That's there. This is part of any microprocessor-based system that's going to have this. This is not unique to the 8086. And I should point out that the 8051 also does something like this if you have to hook up external memory. This is a very common technique to interfacing memory to a microprocessor. That's part of, even though we're not really dwelling so much on this particular processor, this is core. Right here. And this just goes into more details of the same thing. And then we've also got the buffered, which I'm not so worried about that right there. Right there. So, okay, getting into the timing right here. This is what we're looking at in the clock. Now this is the clock, internal clock, and this shows it as a 50% duty cycle, but in reality we know that going into it is actually a 33% duty cycle. This generates these internal right there. But we've got one bus cycle is 4 clock cycles right there. And what we're looking here is that we've got right here our address data. During this part right here, we write the address here, right there. During this time right here, the ALE is going to be high. Before this point here in time, the ALE has to go low because our address bus here has to be latched onto our address lines right here. Then we write our data to memory right here, and we hold it there, and we take the write not line low, and then we take it high. Now, you should note here that it goes high about half a clock cycle before the memory is taken off the bus. Everyone see where I'm talking about? This is where this is going high, right here, and we come here. See, it's still, the data is still on the bus. It's actually following the falling edge of this T3. It's at there, and that is telling whatever device that that we're talking to latch that data into memory. So this timing diagram is very, very important to look at, because when things don't work in hardware, it could be that because you've got between this time and this time for that memory to latch that data. If the memory's too slow, you get write errors. So the same token is you've got from the time our ALE is not shown here, but the ALE would just simply go high here, say high, and go low here. And it would then latch the address onto the bus. So this is a typical write bus cycle right there. This is the microprocessor writing data out to a memory location. This is what's going to happen. It takes 4 clock cycles. We put the address out. It stays there for 1 clock cycle through T1. Our ALE is not shown, but it's going to go high during the cycle, right there. It's going to go low. And then after that, it's going to write the data here, right there. And before the data is taken off the bus, because right here we're going to start the next clock cycle, or next cycle here. Before we take the data off, we want to latch that onto into the memory. So that's our read-write, that's our write cycle right there. And instead, I'm not going to read the book, but I'm using the book so I don't have to redraw all these graphs. It's a lot easier than redrawing the graphs. The read cycle is almost the same. The only difference there is the address line works the same. We latch the address here. We take our read dot line low. This time here is waiting for our memory to put the data out there. And it's got so long before it takes the data out there, because this is the microprocessor telling the memory that I've got the data, you can go ahead and take it off. That's there when we take that line high again. Right there. So the read and the write are slightly different. The difference is that this is coming from memory or I/O. The chart says memory, but it could be an I/O device as well. The only difference between the cycles is that we're not showing the memory / I/O not line, or the memory not / I/O, depending on which processor you're working with. But it's the same basic concept right there. That's our read-write cycle right there. I'm almost, I'm going to talk for an hour here, and I'm winding up to my discussion here. Right there. Okay, let me just continue on here. The read timing is right there. This is the full-blown ugly monster. This is the full-blown ugly monster. Again, what we're looking at right here is, here's the only thing I'm going to show here is here's our ALE right there. Here's our address line right here. We put our address lines here. Notice again, let me draw it from here, right here. Oh, right there. Let me read mode. Okay. Read mode. Put it back in read mode. Right here. Okay. I want to zoom. Okay. Let me just kind of look at it right here. This is my T1 through T2 through T4 clock cycle right here. Right here. At this point here, I put my address right here just at the start of T1. Here's a valid address right here. This is, which processor is this right here? This is the 8088. Let's find the 8086. Where am I going to? Nope. Nope. Okay, let me just go back to that one right there. Again, this is definitely confusing us a little bit, because this particular book is swapping between, but we'll just look at, all right, come on. Right here, let's just look at this right here. All this is saying that our I/O memory NOT line has to be set. It's set there at somewhere in T1. Our address line is set right here at the beginning of T1 right here. This is where here's start T1. It takes this long between the start of T1 till our address is valid. Right here we have a valid address right here. Same thing down here. We have a valid address at this point. Once our address is valid, we take this ALE high. Notice that our ALE goes low while the address is still there. Right there. Now we're going to ignore this A7 through A3 here. We're going to ignore that there. This is our read cycle, so we just look here. Our read NOT, that's the same thing here. The only thing we've added to this right here is the ALE line. That's really the only thing. I would not spend don't spend time on this. Just when you look at this graph here, just realize that the ALE line is also shown right here. It goes high somewhere right around here. It stays high till about here. The ALE line is what's shown there. The simplified is all you need to know. You don't need to know this nasty thing here. This thing is pretty nasty because this has got all the timing that's specified in the data sheet and everything else right there. And that's very important. If you're selecting memory, we won't be doing that. See, there's all those hold times and all these characteristics. We are not going to spend time on that right there. And this is the write cycle. It's, again, very similar. Let me bring this back to the ready and wait state. We're going to skip that. Right here. This is generating wait states. We're not going to be generating wait states. Wait states are used if you have slow memory or slow I/O devices. You'll inject wait states in order to tell it to wait for that memory to catch up. Not very common today. You got to remember this chip was built in 1980 when there was a lot of very slow devices right there. Now, we'll look at this one right here. The minimum mode right here. Right here. This is not unusual, a type of system right here. I've worked with multiple systems like this right here. Well, we've got, this is a complete system for the most part, right there. What we've got here is we've got an 8259 interrupt controller. That's a chip that contains the interrupts. It's got 7 interrupts that go into it, right there. And the whole idea of that is that it will then write the interrupt and to handle all the timing for us if there's an interrupt request. Our interrupt devices don't have to do that. So we have a chip that handles the interrupt. We have another chip over here that does our clock. We talked about that. Does our clock right there. And it's got this is minimum mode, yeah. Clock, ready, and reset right there. The ready you don't necessarily have to have. This is 8088. Here's our address bus, and this is going through our latches. And depending on whether you got an 8086 or 8088, you may have 1, 2, or 3 latches right there. That there. We've got what they call a 8266 transceiver, and all that does is buffer the buses right there. Protects it. There. It's got the output enable, and that's coming from here, and it also comes from the enable from the interrupt controller right there. So we've got some things on wiring that I'm not really getting into detail on this, but that just simply controls who's reading and writing from the bus right there. Now we come here, and what we're not showing here is we've got some lines here. Our read not, write not lines are going read, output enable, read, write not right there. Those are coming off of there. Chip select. The chip selects are showing off the address buses but they're not necessarily showing how they're connected up right there. What we're missing there is the address decoding. Right there. We've got, here's 4K of RAM, here's 8K of ROM, and there's some I/O, peripherals out there is what we've got right there. So that's a basic complete system right there. We're not to the point of completely understanding that there, but that's really what you would see something similar to that in the microprocessor system. You'll see some ROM, you'll see some RAM, you'll see some peripherals tied to the I/O bus right there. We've got the interrupt controller, we've got the bus transceiver, and we've got our address latches right there. And then we've got our clock generator. So this is one of the reasons the microprocessors are not very popular for embedded systems, is how many ICs do we have here? I see at least 2 latches, 3, 4, 5, 6, 7, 8, 9 chips required for a very basic system. If we don't need that much horsepower and we get by with a microcontroller, how many chips do we need? 1, right? But again, some applications require a full 8086 type system. Some don't, right there. As I said, I'm kind of flying through this chapter right there. We won't get into that. This talks about the bus controller right there, maximum mode. Must have the bus controller. That's why I've never used it in maximum mode. You have to add the bus controller to it. And I'm skipping the maximum mode right there. Okay. Questions and problems? This is similar to what you're going to see me give to you next week. What's the difference between the 86 and the 8088? It's CTL compatible. What's that mean? I'm going to skip the fan out. What appears on the address data bus when it's active? I'll skip that there. What condition does 0 on the read not line there? Explain that there. So these are basic 10 questions right there. There's a whole bunch of questions, and I will go through and pick and choose which ones of those that I'm going to hold you responsible for. But they all come out of this chapter. Right there. Because our next chapter, when we look at this, is the memory interface. So we'll probably talk about that a little bit. I don't know if we'll... See, we meet tomorrow again, don't we? We might get into that tomorrow. I think I'm going to quit here at this point for the day. Any questions, comments? A lot of information, isn't there? A lot of information. Out there. I really suggest that you take some time and read chapter 9. That's there. You really need to read that there and look at those questions. I will highlight which questions you need to know before next week, before I leave, before I'm gone next week. That's there. But those are there because the next chapter is actually how we connect the memory to this device. That's there. And then we'll get back into how do we write code. So unfortunately, there is no labs for the hardware part of this class. That's there. The lab would be you sit down with a CAD program and you design a system. And we'll go through that process. Out there. I'll see if I can get a copy of OrCAD. That's the one I'm most familiar with. And go through it how you would wire this up in order to set everything up that there. So all right. With that said, I'm gonna. We're supposed to run till 2 o'clock. I can't go much more than an hour. That's really my programming out there. What do your other instructors run for 2 hours straight now? No, they can't. Some can, huh? And they keep you awake for the 2 hours? Be honest. No. See, I prefer classes. Actually, this particular course I'm used to would meet twice a week for an hour and 15 minutes, twice a week, and then they would have a 2-hour lab period. That may or may not meet unless you have a lab. We don't tutorial sessions. I'm not used to that out there. I'm not sure what we do during a tutorial session. That's there because I haven't really signed homework. We don't have numerical homework problems yet, and we won't have any in this class. So probably what will happen is I'll probably have to go through sample test questions out there. So, But we haven't really got to that point there. We spent 2 weeks on introduction, and this is actually the start of the real meat of the class, right there. So, all right. I'll see you tomorrow then. This group meets at what, 10 tomorrow? Oh, 8 o'clock tomorrow. 8 o'clock. You're my first group, and then the microcontroller is my second group. 8:30, huh? You wouldn't break my heart to show up closer to 8:15, 8:30, because I'll be honest, it's getting here